Hello everyone, welcome back. N3FJZ with more ZX front panel work. Okay, what you see before you is a 74LV8154 32-bit counter chip. And with that, I have now implemented a frequency counter that can count up to 50 megahertz, and it will be part of the ZX front panel. Right now it's very early. I just got it installed and implemented in a basic form. I want to do some additional work on a better input circuit, a little bit more conditioning so that I can eventually make the front panel function as a frequency counter that you can test frequencies, RF frequencies outside of the front panel as almost like a standalone frequency counter. But right now its job is to assist in the calibration of the SI5351's main crystal. As you know, the SI5351 does have the means to trim the master oscillator to put it dead on. And what I've done here is taken this circuit in conjunction with the U-Blocks module and used a circuit design idea that I found on the website of Scott Harden. And he has a project there on his website. Let's see, here we go. It's called VHF frequency counter with PC interface. And on my website, if you go to useful links and go all the way down to the bottom, you'll find my, there's a link there. And Scott's idea. I've essentially copied the idea and then reverse engineered it so I understood what was going on and made some changes in the way the code operates, but it's essentially the same circuit. So my hat's off to Scott. Thank you very much for doing the legwork on this, and this is a very nice feature to have on this front panel. So what it does is the U-Blocks GPS receiver, once it syncs to a satellite, it will start to produce a 1 pulse per second output, and that's the LED on the left that you see flashing. And what that pulse does, it does two things. First, this is a 32-bit counter chip, and the input to this counter is the frequency you want to measure, and the counter is always counting. It never resets. It's just counting. It overflows, starts over again. What the GPS does in the function that this chip provides is that when the GPS 1 pulse per second signal rises, it latches in whatever the count was. So essentially you take a snapshot of what the count was on the binary 32-bit binary counter, and then when the next 1 pulse per second signal rises again, you capture the next count. And what the software does through an interrupt, and that's the red wire you see above the resistor, that then is connected to A11 on the Arduino Mega, and it creates an interrupt. And what the interrupt does is it does the processing for the chip. So what it will do is it will read the count from the 32-bit counter as it is this moment, and then the prior interrupt that happened a second ago, it has the old count. So it subtracts the old count from the new count, and that is your frequency. Yes, there is a point where it does roll over. I don't know if I've gotten code in there that will detect a rollover and do the math properly. But right now it's not a big deal. I think I do. That's the only case where the new count would be less than the prior count. Well, I don't want to get into the details. That's actually in the code, so you could look at that interrupt processing and then determine how that's done. Okay, now the exciting feature here is what I've done is through the front panel software using the user interface, you can go through the different functions, the menus. Here is just, as you know, brightness, contrast for the monochrome display, and then we get into the parameters. Now, what I've done is a quick modification to this screen. It's not the final form, but I had to stick it somewhere. So what we have here is that, as I've discussed before, you set your IF frequency, which is essentially your crystal filter center frequency. And then there was a oscillator trim, and essentially you would just do that blind. You would manipulate that number. Let me get back to the screen. Hit the wrong button. Okay. You would just manipulate that number with the dial encoder until your SI5351 was on frequency. So what I've done here is I've modified it slightly. Now, in the box entitled IF frequency, that's not what that is. That is the 10 megahertz signal I have coming out of clock 1, which is the center, I guess you could call it the center channel of the SI5351, where the clock 0 is the VFO and clock 2 is the BFO. And most SI5351 circuit implementations on homebrew rigs, you leave that center channel off just to eliminate some crosstalk. But what I've done here is I've programmed it to generate exactly 10 megahertz. And then I got the counter chip counting those, that frequency output from that center channel, or channel 1, and it should be 10 megahertz, and that's exactly what we're seeing here. And this really is exactly 10 megahertz as synchronized to the GPS satellite. So as long as the U-Blocks module is doing its thing and the GPS is accurate, of course, that would be the frequency. So the way this works, and again, this is not the final implementation. I'll have something a little bit more polished. But essentially what you would do is you would, just to demonstrate, I'll knock this off frequency, you would use this crystal or oscillator trim value, and you would basically dial it in to get exactly 10 megahertz on the upper display. And I took a big step here. You'll see it's 10 megahertz in 10 cycles. It's at 153, and 253 seems to be the magic number from this point. Now, as this module warms up, that number will change a little bit. So I'm even contemplating maybe even writing in sort of like an auto calibrate feature where it will just constantly trim that SI5351 to keep it dead on frequency based on this 10 megahertz signal coming out of channel 1. But the idea here is that you would just adjust this number, and this is updated once per second. So this is a real frequency counter, so it would be used like any other frequency counter. Once per second it updates, and you just would manipulate that oscillator trim to get exactly 10 megahertz. Well, I found that probably the best setting is where it toggles between 9.999 and so forth megahertz and 10, where it goes back and forth between the two. That would probably be right on 10 megahertz or very close to it. This module's been running about an hour, so the drift isn't as pronounced as it was earlier. But here you see it's toggling between 10 megahertz and 9.99 megahertz. And of course, once you've, if you don't like the idea of that clock 1 running, at some point, once you've set your settings or your trim, oscillator trim to where you want it, where you're getting a stable 10 megahertz, you come down to the CAL, I call it CAL clock 1, set that back to 0, and let's go back through that page. You'll see now that the frequency counter is reading 0 because there's no output from that pin. And something interesting I discovered, which I can't do right now because I have the connector soldered on, but what I was doing is I would disconnect the input to the chip and just hold the wire in my hands, and then you'd see it measure 60 cycles. So that's pretty cool. So I'm quite excited about this. The chip is about $1 from Moser, and GPS module, I think you can get these for under 15, definitely under $20 now. And that course also runs the real-time clock, which I featured in prior videos. Okay, another feature I've added is, if you look above the frequency, you see a G and an E. The G stands for general class, E stands for extra class. And what, this is very early too, I want to probably include other license classes in the logic here. But the way this works is the frequency you see on your dial, you would have to be an extra to have privileges to transmit on that frequency. And of course, at 3.8 megahertz and above, a general class would have that privilege. What I want to do is expand this to include all the license classes, including the ones before the for the change. About a decade ago, you had I think it was advanced and novice, and include all that there too, perhaps, and maybe squeeze in what is the mode you're allowed to run. Anyway, that was just something that I thought was a nice feature to have, since you got a computer doing it and you can have a lookup table to look at the frequency. So I'm quite excited about the frequency counter, because you can put your SI 5351 right on frequency, right from the front panel. Of course, first I'll have to turn the output back on, and you can see here on the scope. Turn it off. Bring it up to 2, 4, 8. That seems to be stable. And on this scope, you can see the top trace is the 1 pulse per second rising. That triggers, that, as I said before, that latches in the count of the counter into the registers that the Arduino can read from. And the trace you see on the bottom is the one of the 4 registers. So when you lock it into the chip, you have essentially an 8-bit bus, and you have to read that 32-bit number in 4 chunks. And what you see at the bottom there is just one of those lines pulling low. So the interrupt occurs, rising edge, interrupt then starts reading those registers, and that's register 1, and there's 3 more after that. And that's that little falling edge you see there, that lower trace that clocks in with a low. So that's Arduino reading the first register, and then if I had several more traces, you could see each one in turn reading that. Okay, so now that the output's back on, I'm going to go back through my functions, and boom, there we go. Oscillator trim, and now that we have that 10 megahertz channel turned back on, we see what the output of that SI-5351. And the theory here is that the oscillator trim feature in the SI-5351 applies to all the clock outputs. So if you adjust one of the clock outputs for the frequency and adjust the trim, it should then be accurate for the other channels as well, from what I've read. Anyway, I hope you enjoyed this video as much as I enjoyed building this circuit. I've got the new code up on the on my website, and let me get back to that. Just so, here is the in the schematic you see where the 74 LV 8154 is attached to the Arduino, and there's the D the D0 through D7 is the one that is the 8 bits from the chip, and then of course the R1 through R4 is the 4 chunks of the 32-bit value being read can be selected to run on that bus. So with so what you do is that the Arduino the digital pin 37, 36, 35, 34, each one of those would be pulled low in turn, and then when it's low, that particular segment or one of those 8-bit registers inside that counter chip are then presented on the data bus. And you see the GAL, GAU, so forth. That's they call it a gate A low, gate A upper, or the lower byte, upper byte, and then gate B lower byte, gate B upper byte. And then the chip is actually two 16-bit counters, and when you connect pins 8 and 9 together, you then extend it into a 32-bit chip. It's all in the data sheet. Pretty interesting stuff. And again, I want to thank Scott for the work that he did in pioneering this circuit. And of course, above it, you see the A11 Arduino. That's the 1 pulse per second gate coming out of the U-Blocks module. And when it rises, you see the pin 7 on the counter chip and the little rising edge symbol that says I lock in the count. And of course, it also triggers an interrupt on the Arduino. It's an PCINT, which stands for Pin Change Interrupt 19. And when that fires, the code then does some logic to find out was that a dial encoder event or was that a 1 pulse per second event, and it makes through some checking of the actual pins on the Arduino can make that determination. Anyway, code's there, download it, build the circuit, have a blast doing this stuff. All this for me is like a dream come true. I remember in 1974 and 76, before I became a hand, just getting involved in digital electronics. Matter of fact, back here, this digital clock I built in 1976, and it's been running continuously since then. This was my first digital kit project I assembled. And then I got my Apple II computer, and it was all downhill from there. Anyway, 73, everyone. This is N3FJZ.
Hey, well, if I want RF, I'll just buy an Elecraft or try maybe a Flex.
I don't know why you'd have RF problems with a Flex.
The Flex just didn't have good audio. It had some dirty transmit, and that's kind of known. But yeah, the Elecraft was definitely bad.
Flex with dirty transmit? Are you kidding?
No, seriously, yeah. Yeah, the new the 6000, 6400s and stuff, they have artifacts rough on the transmit, yes.
That's the first I've heard of that.
Well, read up on the user groups, Jim, educate yourself.
Why would I want to do that?
Well, you could be smart like me.
Uh-huh. Oh, God.
Yeah. That's one of yours, right?
Absolutely.
Nothing.
Okay, here you see the SI-5351 that we're measuring, and that clock 1, that little coax cable in that center of those two above and below it, well, that's where the 10 megahertz signal is coming out, goes back behind the board, snakes across the bench behind the soldering iron, and through this other mess of wires, and it eventually ends up to where the counter chip can get a hold of it. Anyway.
Yeah, Tootie and those guys.
Tutti Frutti Balooty.
Yeah.
Yeah, roger that, man.
Picture of normal, whatever that is now. I think the normal is shifted, and we'll have to see if normal ever becomes, the old normal ever becomes the new normal. Maybe after vaccines are developed.
By the way, this is AM that I'm receiving here now. And I've found that the SI-5351 is stable enough in the short term to tune right onto an AM signal, right onto the carrier, without a lot of artifacts to be able to listen to it.
I use the Tentec Jupiter as the receiver when I'm not using the SDR. And the Johnson Ranger, that had some tips, and somebody was talking about the Ranger. I forget who it was, but somebody was mentioning it. Maybe Greg, I'm not sure. But anyway, yeah, this is a Johnson Ranger 2, highly modified. I modified it probably about 25 years ago, and I have had, knock on wood, it's going to quit now. I have not had a single failure with it in 25 years, so it's permanently modified for low power. I run the 6146 off of the...
And here you can tell it's AM because I'm switching between upper and lower sideband, and you hear absolutely no change.
The filter reactor, and I get it's a little bit more than the original voltage, but it hasn't hampered any of the other operation. And it gives me about 18 to 20 watts of RF output, which is perfect to drive the 3500Zs. The output power varies from band to band, but nominally I get about 350 watts out with 18 to 20 watts of drive.
Okay. Again, 7 through everyone, N3FJZ.